Alrighty. Okay, so I've changed a few settings. Hopefully this should not cut out in the middle of the broadcast. If it does, bear with me. I will be right back. Okay, so let's get to it. Last class, we started talking about how relational algebra is implemented in Spark. And we started talking a little bit about how we can implement algorithms that implement specific parts of a relational algebra plan. Today, we're going to go into that in a little more depth, though I'm going to describe things a little bit more abstractly from Spark. We're going to talk about kind of just the algorithms in Okay, I guess the changes I made did not work. If this keeps up, I may end up changing technology for the course. Apologies. Changed a few more things. We'll see if this all works. If it doesn't, well, we'll figure something out. Okay, so let's try this again. So we're going to talk about algorithms for this course, and we're going to talk for relational algebra, and we're going to talk about it in the abstract. Before we get into that, a couple of bits of news. So homework 1 was assigned last night. It is going to be due next Wednesday night. Checkpoint 1 was posted last Sunday. I am expecting submissions to be open tonight, and that's going to be due in about 3 weeks. This is a local technology problem, not a YouTube problem. Some hardware here is not behaving properly. Any rate, moving right along, uh, the we talked about a couple of different ways of evaluating queries last week. We talked about taking every layer in the relational algebra tree and evaluating just every layer one at a time, computing the entire collection uh, uh, obtained by a table scan, computing the entire collection um, from a selection, from a projection, just going bottom up in the tree and just computing the entire collection there. We also briefly talked about using iterators. This is often called volcano-style evaluation after the first system that implemented this particular approach. And then the final approach that you'll see in database systems is called push style, where each operator is kind of its own process, and the operator continuously reads tuples from its input and produces tuples for downstream downstream operators. Now, we already established that this bottom-up approach is not exactly the right way to go. It's pretty much just going to consume a ton of memory. And we also, we're going to talk about push style a little bit later in the class when we get to stream processing. So today, what we're going to be focusing on is this iterator style approach. Now, with respect to these algorithms, there's we want to we're going to get into the details of how to optimize queries and how to model the cost of a query in a little more depth in a couple of lectures. But something that you should be thinking about anytime you're given an algorithm is the uh, amount of CPU that the operator is using, as well as how much memory it consumes. And something you might not be used to, but that is relevant here is how much disk I/O it's using as well. Um, Now, as far as databases are concerned, usually the limiting factor is going to be the amount of memory or the amount of I/O that a particular algorithm is using. CPU is important, but usually does not end up being the limiting factor just because all of what we're doing involves data. Right, so so let's talk about memory and I/O. So with respect to memory, we're not really interested in, we're really interested in memory from a very coarse perspective. We're not really looking at the amount of memory, we're not really looking to compute the precise amount of memory that the algorithm uses. Usually what we're looking at is to bucket the algorithm into one of several different bins so that we can kind of essentially how we treat the algorithm depends on which of these bins it falls into. And at least for a lot of operators, the algorithms associated with those operators use only a constant amount of memory, not and not really a variable amount. So those are kind of, that's like the ideal case. The amount of memory might also scale with the size of the output. We'll get into this a little. You'll see some algorithms that have this fall into this particular bin a little bit later in the semester once we start talking about aggregation. The amount of memory that the algorithm uses might also scale with some part of the input, and we already saw a little bit of an example of this with joins. We'll get into that example a little bit later in this lecture as well. Now these are kind of the three sort of good bins. If it's constant, that's fantastic. If it scales with the output or part of the input, that's tolerable because at least there's some chance that those are going to be small enough that they'll actually fit. If it's any worse than that, we really don't care. Anything worse than that is basically an algorithm that doesn't really help us. It's not always the case, but at least for the most part, everything that all of the algorithms that we're going to be looking at either are constant size, they scale linearly with the size of the output, or they scale linearly with the size of the input, or at least part of the input. Okay, so that's memory. And the main thing we're looking at when we try and understand whether what the memory consumption of a particular, the memory requirements of a particular algorithm are, is whether we have enough memory for that operator. Because really, at least with respect to this part, all we really care about is, does the system have enough memory to be able to support this operator? If it does, fantastic, we can use the operator. If it doesn't, then the operator is useless and we don't really want to consider it. Okay, so the other part of this exercise is the part of cost modeling here is the number of the amount of I/O that the operator is going to be required that the operator is going to add to our computation. So essentially what we're trying to do is figure out for the entire query plan how much I/O is that operator going to use. So there's a couple of different ways that we could measure this, so that most production database systems are actually going to look at the total number of IOs that the process uses, that the operator uses. Just the number, this operator is going to read X bytes in and then write Y bytes out to disk. For our purposes here and in probably a lot of different, in some of the simpler systems, we're only going to look at the number of just the number of tuples that an operator has to write out to disk and read back into disk. Because, I mean, this is a reasonably close approximation, but it also saves us having to figure out, well, how many bytes does it take to store a string? How many bytes does it take to store an integer? There's a lot of added complexity that, at least from a conceptual standpoint, a conceptual approach to analyzing the algorithm is not particularly helpful. So we're going to focus largely on just measuring the number of tuples that have to be written out to disk and read back in. Again, production database systems are going to take one, like Postgres or Spark, they're going to take one extra step there and actually tell you how many bytes, or be able to compute how many bytes get read and written. Okay, so the part of I/O management that's a little bit tricky is that some of the operators essentially piggyback off of the I/O of another operator. We'll see a couple of examples of this in just a moment, but essentially the point is that each individual operator, we're going to look at each individual operator and figure out how many IOs that specific operator contributes to the total query plan. This gets a little bit tricky, but we'll go through a couple of examples, so hopefully you'll understand. If not, please speak up. I'm keeping an eye on the chat. So again, to emphasize this point, for each operator, we're only interested in how many IOs that specific operator adds to the plan. And then we can take the total number of IOs for the entire tree and then just sum them up to get the total cost of the entire plan. Okay, one other note before we get into the algorithms themselves. So far, I've been kind of sweeping something under the rug, lying a little bit. I've been pretending that, at least implicitly, even if I haven't explicitly said this, that every single operator has one algorithm associated with it. And started just pretending that there's one canonical algorithm for every single operator. And in general, that's not true. There might be multiple different algorithms, and we'll actually see an example of that today when we talk about joins and Cartesian products. Um, Also, in many production database systems like Spark, there might be some algorithms that cover multiple operators. The really trivial example of this is Cartesian product combined with selection gives us a join, which, as we'll discuss today, actually has we can be a little more clever with picking an algorithm for a join than we can for just a Cartesian product and a selection. So in Spark, there's this concept is captured by what it calls a physical plan, which is nodes in a physical plan essentially capture multiple different operators, and they correspond directly to a specific algorithm implementing those operators. For our purposes in this class, we're not going to be dealing with enough different algorithms. We're not going to be dealing, the complexity of this particular project is low enough that we don't actually care about that. And as you create the iterators, it's perfectly reasonable to pick the specific algorithm that you're going to be using as you're creating the iterators. You don't have to go through this extra, or there's not going to be much of a benefit to going through this extra step of building a physical plan. But when you hear the term physical plan, you should at least know that this is what we're talking about. Okay, so let's, any questions so far? And if not, we will get to the, algorithms themselves. All right. So we're talking about every single relational algebra operator, and that begins with the leaves of our relational algebra trees, the tables. So what if we're building an iterator over a table? We're going one tuple at a time. We're reading one tuple out of a CSV file, and we're spitting it back out. Reading the next tuple of the CSV file, we're spitting it out. Next tuple, and so forth. The details are maybe a little bit different for other storage formats, but essentially the idea is pretty much the same. So for a full table scan like this, how much memory do we need? Which of the three buckets does a table scan fall into? Constant. Great job, Karan. Yeah, so the amount of memory that we need here is fixed. We're reading one tuple out of the file, and we're spitting it out. We're passing it on. We never need to look at more than one tuple, or if we're being honest with ourselves, a buffer, a small buffer of tuples at a time. How about IOs? So obviously we need to read the entire table in. So that's the number of tuples that the table scan operator is going to add. Okay, so table scan is kind of the trivial case. Let's talk about, oh, there's a question. Deepak asks, reading n tuples at a time and processing the batch versus reading one tuple at a time. So, okay, even if you implement a table scan as reading one tuple at a time and spitting it out, reading the next tuple, spitting it out, and so forth, the underlying file system will actually do some buffering for you. If for no other reason than usually you can't read data off of a disk at the granularity of individual tuples, you have to test. All right. I will be picking a new technology over. All right. Let's. So to answer the question, the even if we read multiple, even if we are only reading one record at a time, we'll still end up producing um, we'll still end up essentially reading multiple tuples at a time just because the underlying system, the file system, um, usually only lets us read a chunk of bytes at a time. So we'll end up reading an entire chunk of data. And then even if we're only scanning over that tuple over that chunk to parse multiple tuples out, we'll still have read the entire chunk in. So to answer your question, Adesh, the we'll still essentially end up doing some buffered reads, and um, regardless of how we do it though, we'll still end up reading the same number of tuples off of disk. Okay. So moving on, let's talk about some, so we kind of introduced the algorithm for select last class. Let's kind of recap what the algorithm needs to be able to do. So at the very beginning, we call get next tuple, or we're calling the function to get the next tuple out of the selection operator. The selection operator basically needs to read one row from its input. And then essentially one of two things at that point can happen. The input might have another record to read, or it might not. Let's assume that there is another record to read from, another tuple to read from the input. So if that's the case, we're going to check to see whether that tuple satisfies the condition that we're being asked to satisfy. And if so, great. We're going to return that record. If it turns out that the condition is not satisfied, we're going to try again. We're going to go back to the very beginning, read the next row, and then produce repeat the entire process. Check the condition and return the row if satisfied, and go back again if not. The other possibility here is that the condition is not just not satisfied, the other possibility is that instead, when we try to read the next row, there's no more rows to be read, in which case the selection is done, and we can tell the next operator above us that there's no more records to be read as well. So this is a really basic state machine for the next operator in the query. The next operator in the selection next function in the selection operator. And let's ask ourselves how much memory is required here. In the interest of time, since it's been technology problems, I'm just going to say, so the selection operator, at no point in here are we ever storing more than just one row. So the amount of memory it requires is constant. And additionally, the amount of I/O that the selection operator itself adds is nothing. It's reading tuples from its input, and that input might add some cost, but the number of IOs that the selection itself adds to the total cost of the plan, there is no, it does not write anything out to disk, it does not read anything in from disk apart from what its input has already read. A quick example might help to illustrate this. If we have 100 tuples in R, then we're going to need 100 tuples worth of I/O to compute a query that is just a table scan, select star from R. On the other hand, if we have a selection on top of that, it's still going to take 100 tuples of IO because we have to read in all of the tuples in R, and the selection itself is not going to add anything new. So R is 100 tuples of IO, but select of R is also 100 tuples. So the select itself is not adding anything new. Okay, projection. Project of R is going to start by reading a single row. If there's a row to be read, it's going to project out the relevant attributes, and it's going to produce a new row. And it's going to return it, even simpler than the selection. If there's nothing else to be read, then there's nothing else to be read. We're done. And just like selection, this doesn't add any new memory requirements and doesn't add any extra IO because again, we're reading only one tuple at a time. We're only ever looking at one tuple at a time. And all of the IO that might be needed for a query with a projection comes from the operators below it. Again, let's assume that we have 100 tuples in R. Computing the projection of R is still going to be 100 IOs, and computing the projection of a selection of R is still going to be 100 tuples worth of IO. So, to emphasize this point, projection and selection never add new IOs. Okay, union. This is also a relatively straightforward operator. We talked about this a little bit last class. So we're going to look at the left-hand side. We're going to look at R and read the next tuple out of the iterator over R. If there is another tuple there, then we're going to return it. Good. If there is no more tuples in R, we're going to move over to S. If there's a tuple in S, great, we're going to return it. And if there's no more tuples in both R and S, then we are completely done with this entire process, and the union iterator has no more tuples as well. And once again, this just like the previous two cases, we're never looking at more than one tuple from either R or S. This is a constant memory requirement, and the union itself is going to piggyback off of the IO costs of its input operators, so we're not adding any new costs as well. Questions so far? Give a few moments. And okay. Cartesian product. So of all of the iterators that we're going to be implementing for checkpoint 1, this is probably the one that is the most, the least straightforward. Now, the tricky thing with Cartesian product is that for every tuple of R, we're going to have to iterate over all of the tuples of S. You could, of course, flip those, but just for simplicity, I'm going to assume that we're iterating over all of the tuples of S for every tuple of R. So that means test. All right, I'm hoping I can go another 20 minutes without this breaking. If not, I have a backup plan that I'm getting ready to deploy. All right. Where are we? Okay. So cross product is a little bit tricky because for every tuple of R, we have to go over every single tuple of S, which in other words means that every tuple of R participates in multiple output tuples. In other words, every time we call get next, we're kind of going to have to save that tuple of R so that we can use it for the next tuple that we return. So the first thing we need to do when we are asked to produce another tuple out of the cross product is decide whether we've already saved a tuple of R from a previous call. Obviously, this is the first time that we've gotten a tuple out of the cross product, so we don't actually have anything left. We're going to read a tuple from R and ignore the other part here. We'll get back to that in just a moment. Okay, so now we have a tuple from R. So the next thing we need to do is get a corresponding tuple from S. We're going to read a tuple from S, and assuming that sorry, I'm skipping a step here. Assuming that there is a tuple to be read out of R, then we read the first row of S. And assuming that there is a tuple to be read out of S, then we're going to take the two tuples, we're going to smush them together, and that's going to be the result of the Cartesian product, R cross S. Okay, so we've got R cross S. That's our first record. Let's go back to the beginning. Now, the next time someone comes along and asks for the next tuple out of this iterator, we're going to check to see if we have an R from a previous iteration. We're going to check to see whether we have an R from a previous iteration. This time around, we do. So we're just going to skip directly to reading the next row from S. And once again, we're going to, assuming that we get a record out of S, we're going to smush it together with the R that we've previously read, and we're done. Now, if at any point we read, if it turns out that there are no more records to be read out of R, well, we're done. This is the outer loop. We've gone through the outer loop all of the times we're going to go through it, so there are no more tuples to be produced. If, on the other hand, we read the last tuple out of S, that just means we finished the inner loop. So we're going to go back, we're going to reset S, we're going to go back to the very beginning of the stream of tuples in S. We're going to read the next row out of R, and then we're going to start the whole process over again. So this is essentially modeling this two-level loop where we have an outer loop over all of the tuples of R and then an inner loop over all of the tuples of S. An inner loop over all of the tuples of S. And am I skipping something here? Yeah. So now, how much memory do we need to be able to pull this off? Well, as it turns out, this is actually a deeper question than you might think. And how much memory and how much I/O is required here actually depends on the specific algorithm that we choose to implement this with. And what it boils down to is, well, we're going to have to iterate over all of the tuples in S multiple times. And the question here is, how do we reset S? How do we go back to the beginning of S and replay all of the tuples that we've gotten from there? And there's a couple of options we have there. So the first thing we could do, let me back up. So Debbie asks if it is safe to say that the table scan is what really requires IOs, and since the data is read or buffered, that a given operator, all a given operator does is return some rows based on the conditions. That is completely correct. Sorry for not noticing that until now. That is completely correct. Up until the cross product. For selection, projection, and union, those operators add no new IOs. They just kind of piggyback off of everything else. The cross product is where your question gets a little more interesting. Because once again, the problem here is that we're going to have to iterate over all of the tuples in S multiple times. So how do we go back to the beginning? Now, the simplest approach here is to take all of S and just stick it into an array list somewhere and be happy with that. This is really nice in terms of I/O because we're only paying the I/O cost of executing S once, but comes at a bit of a penalty, because now we have to, because now, one second, because now we're reading all of S into memory. Now we're sitting there with every single tuple in S sitting in memory, and so we need to, we're actually paying that memory cost. And maybe it turns out that we don't actually have enough memory to be able to pull that off. Maybe we don't have enough memory to be able to pull that off. So what are our options here? Option number 2 is to rerun the entire iterator from scratch. The downside to that is, well, now we're paying the cost of rerunning that entire iterator from scratch multiple times. So if S has some cost, let's call it cost of S, then we're already paying that once, and the cross product operator is going to have to read it. Essentially, so we're paying the cost for the first scan already. We're accounting for the first pass through S already. And it's going to, instead, the cross product is going to have to run S once for every single tuple in R. And that is kind of painful. So rerunning the entire iterator is going to add, we're already paying for the first run through S. We're going to add one extra run for every tuple in R, except for that first one that we've already paid for. Now, another possible approach here is that we take all of the tuples in S, and as we read them in that first time, we're going to write them out to disk. So this has the downside of, well, now we actually have to write things out to disk. So we're going to write S tuples out to disk, and we're also going to have to read those back in. Okay, Ben asks, how does bag versus set affect the flow of reading from? Okay, we're going to go with something. We're going to try something a little bit different here. Okay, I'm going to hope that this works. We'll see. Okay, so the question here is, once again, how do we reset S? We can either materialize S, we can rerun the entire iterator from scratch, or we can materialize S onto disk. And this is, in general, going to potentially get very expensive. So let's do a couple of really quick examples here. I'm going to hope that folks are, hopefully this is not echoing anymore. And you're not able to see my desktop here, are you? Oh, that is annoying. All right. See if we can rig up a really quick fix here. This is going to be annoying. All right. Oh, right. Of course it's not going to work. Okay. I really hate to do this. I'm going to...
All right. Can I assume that everyone can hear me here? Speak up if you can. All right. Perfect. All right. Let's see here. Okay. So, moving right along. Let's go through a couple of really quick examples here and assume that we have two tables, both with 100 tuples. In order to, so how many IOs do we need to compute this? Well, in order to get an iterator over all of the tuples of R, that's going to cost us 100 tuples of IO. Getting an iterator over S is going to cost us another 100 tuples. And getting an iterator over the union of those two iterators, assuming that we've already paid the cost for those initial two iterators, is, well, we're not actually adding any overhead there. That is it. We've already paid 100 plus 100, and the union is not going to add anything new. Let's do another really quick example here. R, let's assume that has 20 tuples in it, and S has 100 tuples. Now the question is, how many IOs is it going to take us to compute R times S? So getting an iterator on R is going to cost us 20 tuples of IO. Getting an iterator on S is going to cost us 100 tuples of IO. Getting an iterator on the cross product, again, assuming that we have iterators on the prior two, well, how much does that cost us? That depends on which of the three algorithms we choose to use. If we can fit all of S in memory, fantastic. We are not paying any extra IO here. If we need to replay the iterator, well, then we're essentially adding a bit of overhead. For every tuple beyond the first tuple of R, we're going to add the entire cost of S again. So remember, we've already paid 100 tuples for that first scan. For every subsequent scan, we're going to pay another 100 tuples. There are 19 tuples in, there are 20 tuples in R. We've already paid for the first of those, so 19 more copies of S is going to give us 1,900 extra tuples. Caching everything on disk, well, for the first tuple of R, we're going to read in from S. We get that for free, but then we also have to write all of the tuples in S out to disk during that first pass. So that first one is free to read it in, but we're going to have to write it out, so that is an extra 100 tuples, because that's the size of S. And for each of the remaining 19 tuples in R, we're going to have to read in those 100 tuples back in from disk. So that is 1 times 100 plus 19 times 100, in other words, 2,000 extra tuples. Now, looking at each of these algorithms, the one that seems like it's the best option is to replay the iterator from scratch, because that's going to cost us the initial 100 for S, the 20 for R, and then the extra 1900 that we get from replaying. Okay, now let's assume, let's continue the same assumption. We have the same 20 tuples from R and the same 100 tuples from S. Now let's assume we also have a selection predicate that allows us to filter out 90% of the tuples in the in the cross product of R and S. So now how many IOs do we need to be able to compute that crossed with all of the tuples in R? Now how do we get that C filters out 90% of the tuples? We'll talk about estimating that sort of thing in a couple of classes. Here, we're just going to assume that we know that up front. Okay, so we've already established that getting an iterator over R cross S is going to cost us 2010 tuples worth of I/O, and the selection is not going to add anything new. So the selection applied to R cross S, getting an iterator on that is going to be the same 2010 tuples. Getting an iterator on R, because again we need that iterator for the cross product, is going to be another 20 tuples over what we've paid so far. And getting an iterator over that entire expression, over that entire cross product, using the operators that we've already computed, well, that is going to depend on which algorithm we use. So one algorithm there is just let's put everything in memory and we're done. Now that's the easy case, but obviously that doesn't always work. So one option, again, would be to replay the entire iterator over and over and over again. Now there are 20 tuples in R. We've already accounted for the cost of one of those, so the cost of the remaining, of replaying for the remaining 19 tuples, well, let's go back. The cost of running that entire iterator from scratch was 2010. So rerunning the entire thing 19 more times is going to cost us 38,190 tuples worth of I/O. That's a lot. The other option here is to write everything out to disk, and for that we need to be able to estimate how many tuples there are in the selection applied to the cross product of R cross S. Now, the size of R cross S, we know that there are 20 tuples and in the on R, 100 tuples on, sorry, there's 100 tuples. My math here might be a little bit off. No, it's not. There are 10 tuples in R. There's 20 tuples in R. There's 100 tuples in S, which means that in the full Cartesian product of those, there are 2,000 tuples. We also know that the filtering condition is going to filter out 90% of those. So what we are left with is 200 tuples. And we're going to have to write those out once and read those back in 19 more times. So there's 200 tuples per each of those events. There's 20 such events. So we're going to end up doing another 200 IOs of write, another 3,800 IOs of reads, which totals up to 4,000 extra tuples of IO either in or out. We're not going to make a distinction there. In other words, if we look at these different options, now the best option is actually different. Previously, the best option was to replay the input operator. In this particular case, it makes more sense to cache because, well, we don't have to pay that 38,000 cost. We've essentially filtered out a bunch of tuples. It makes sense to save the work that we've done so far and reuse it. So the best option here, we're going to pay the initial cost of computing select from R cross S. We're going to pay the cost of iterating over the tuples in R again, and then we're going to pay an extra cost for caching tuples in and out. Okay, so we've kind of introduced so far some fairly naive algorithms for implementing Cartesian product. Can we do better? And in order to understand how we can potentially do better, it helps to visualize what this algorithm is going to look, what the algorithm looks like. So with nested loop join, what we're essentially doing is we're reading one tuple in from the left, one tuple in from the blue table, and we're joining it against every other tuple from the red table, which means we need to scan over all of the tuples in the red table once. Then we read another tuple in from the blue table, and we scan over all of the tuples from the right. We do that over and over and over again, and we're essentially repeating ourselves. We're going over all of the tuples on the table in the table on the right, just over and over and over again. So in other words, the problem is that for every tuple we get in on the left, we have to scan everything on the right. So one common trick, one common optimization, and if you take away no specific algorithms, specific details from this class, there's a bunch of kind of common tricks that databases brings to the table. And one of those common tricks is work sharing. So we're doing a ton of work for every single tuple in the left iterator. And one trick to making this faster is to do that scan. We still have to do that scan, but maybe we can do that scan and kind of share the work for that scan from multiple tuples in the left. And the way we can do that is to create blocks of tuples. So we're going to read in a block of tuples from the right. We're going to read in a block of tuples from the left. We're going to read in a block of tuples from the right. And then we're going to compute a full Cartesian product just within that block. Because we've read a relatively small amount of stuff into memory here, it actually saves us from having to do the full amount of work that's, we don't have to do any extra I/O as long as we are staying within those two blocks. And that's why this is referred to typically as block nested loop join. So the previous algorithm, the more naive version of this is just nested loop join because we've got one loop nested inside another. And here we're dividing the contents of each of these streams into blocks. And then we're mapping, we're pairing, doing a nested loop join between all of the elements of the first blue block and then all of the red blocks, then the second blue block and all of the red blocks, and so forth. And this is saving us. We're still repeatedly scanning all of the tuples in the red blocks, but this is saving us a bit of work because now instead of scanning the entirety of the red table for every single tuple in the blue table, now we're scanning it for every block in the blue table. So if we pick a particular block size, and assuming that we're going to cache S to disk, we're adding a little bit of a memory overhead because now we actually have to store that chunk of R and that chunk of S. And this is going to still involve a bunch of I/O because, well, the first block, we're going to read in S once. We're going to pay that get that cost already paid for, but then we still have to write everything out. And then for every subsequent block, we're still going to have to read everything back in. But as you can see, this is actually this can be significantly lower than just regular nested loop, because now instead of iterating over literally every tuple of R, now we can create a block of a couple of hundred, 1,000, or even more tuples from are and just iterate over those. And you can kind of think of the in-memory caching approach that we discussed earlier as kind of a special case of this, where the block size is the same size as one of the two tables, where we read all of one table in and then we just join it against the other. Okay, we are running quite a bit late due to technical difficulties, so let me get into the last bit here that I want to talk about. So cross product, computing the Cartesian product, no matter, question. Block nested loop is similar to partitioning the table. Yes, we'll actually get into this in just a moment. Hopefully we will have enough time. But yeah, we're essentially partitioning the table into blocks. But we're for block nested loop join, we're not doing any sort of intelligent partitioning on it. All we are doing is taking the first 100 tuples, then the next 100 tuples. But yes, we can do way, way, way better if we know that some of those tuples are going to get immediately thrown away. And that gets me to the next question, the next thing I wanted to talk about, which is joins. So Cartesian product is, no matter how you slice it, you're always going to have to pay an n squared cost because there's going to be n squared tuples that have to be produced. But if you know that the very next step is going to throw away a large chunk of those tuples, maybe you can do something a little bit better. Or to visualize this, for every, if we have our blue table and our red table, the cross product is basically has to produce every single pair. But if we know that we have some attribute on the left and some attribute on the right, and we're only looking for the pairs where the two attributes are the same, then we're in luck, because we might be able to throw away some portion of our input, or at least scan over the input in an intelligent way that allows us to ignore most of the work that we need to do. Unfortunately, with just regular cross product, if we don't actually know anything about how the inputs are organized, then we don't actually have the ability to throw any work out, because at least in principle, any input any blue input could pair up with any red input, at least until we've had a chance to check that pair. So if we don't know anything about how the input data is organized, we don't have the information that we need to throw out any of this work. Ideally, we'd like to be able, so even if we don't actually know anything about the input, maybe we could get some benefit by first doing a pass over the inputs to organize the data, and then once the data is organized, then we can do this this join quite a bit more efficiently. And if the amount of work that we put into organizing is lower than the amount of work that we save, then this ends up being a win. There's a couple of different ways of pulling this off, and I'm going to talk about 3 of them today. What I call an in-memory index join, or you might hear the term one-pass hash join, or just hash join, or in-memory hash join. One strategy that I'm going to call partition join, which is also often called two-pass hash, external hash, grace hash. There's a bunch of different names for it. Or what is commonly called sort merge join, and we'll get into each of these in just a moment. Before I get to that, we're going to need to know what a hash function is. And there's a ton of background. In the interest of time, I'm just going to skip to the 2 main points that you need to know about hash functions. First off, hash function is a function that takes an arbitrary thing as an input. It smushes that thing in various ways, shapes, and forms, and then spits out a number. To be precise, if you take the mod of a hash function's output, it spits out a number between 0 and n, and if your hash function is implemented well, there is no way to predict the number that you will get, or it is, you can think of it as essentially, from a statistical standpoint, it is a random number. But the gimmick is that if you give it the same input, you're always going to get the same quote unquote random number as an output. So we can use this to organize data into buckets. And that's the idea behind one-pass hash join. So essentially with one-pass hash join, we're going to scan over one of the two input tables, and we're going to build an index structure over it. We'll get to indexing in a little more detail in a couple of lectures, but the basic idea is we're going to read one stream of inputs, we're going to shove the contents into a hash table, and then that's going to make our lives easier. So how is a hash table implemented? Well, it creates one of several different, it creates an array of buckets, and the elements in a particular bucket are all of the elements that hash to the corresponding value. So if our hash function has two outputs, 0 and 1, let's say the number 1 hashes to the 0th bucket, we're going to put the first record there. Let's say the number 3 hashes to 1, we're going to put that into the 1th bucket, and so forth and so forth. And once we get to the end of the first input, we basically have this nice little well-organized hash table with all of the records in that first table in it. So now we can scan over all of the red tuples. We get the tuple 3, and we know that 3 hashes to 1. So we only have to compare that 3 against the elements of the 1th bucket. Same thing when we get a 2, we know that hashes to 0, so we only have to compare it against the 0th bucket. And so forth and so forth. And as we scan over the elements of the red table, we only ever need to compare it against the elements from the corresponding hash bucket. Now this is one of the rare cases where CPU actually is important, because at least as far as I/O is concerned, this is the same as the in-memory nested loop join. However, in terms of CPU usage, now instead of doing something n squared, we're essentially doing something that is maybe a little bit more than linear. If we pick a large enough hash table, this is effectively linear. And it's called one-pass hash join because we're taking one pass over each of the input data sets. We scan each of the blue tuples once, we scan each of the red tuples once, and we don't need to do any extra I/O. This is really nice in terms of I/O, but it does require us to keep everything in memory, and it also means that we can only support join conditions that have an equality predicate, because, well, the hash function doesn't really allow us to filter out things, anything else. So you could also potentially, well, I'll skip this in the interest of time. So two-pass hash join is a slightly more involved version of this. The idea is going to be the same. We're still going to hash everything. Which doesn't seem to be loading. Try this again. So the idea here is quite similar, in that we're going to build a hash table, and more precisely, we're going to build two hash tables here. And we're going to build two hash tables, only instead of storing these hash tables in memory, we're going to store them on disk. And the advantage here is that we only ever need to keep a small buffer of tuples for each of the hash tables that we're writing out to disk. And as soon as that buffer fills up, we flush the contents of that buffer out to disk, and then we have the memory for that buffer back again. We're going to do exactly the same thing as before. We're going to take all of the blue records, we're going to dump them out into a hash table, but again, the idea here is that this hash table is now on disk rather than in memory. The other difference is now we're going to do exactly the same thing for all of the red tuples. We're going to scan over all of the red tuples and build a separate hash table containing all of those. And again, those are going to be stored on disk. And the gimmick here is that we're guaranteed that the only matches that are possible are between corresponding buckets, because those are the values that hash to each other. So we can load in one pair of buckets, do an in-memory join between those, and as soon as we're done with that, there are no other ways that we know that there are no other ways that we can join tuples in either of those buckets. So we can throw those back out, we can load in the next bucket, join all of those tuples, and again, we're done. The advantage here or the major advantage here is that this is going to support, this is not going to require as much memory, because we only ever need to load in one pair of partitions at a time. But it does have a much higher I/O cost, because now we need to write all of the tuples out and then read them back in. In other words, we're doing essentially 2 scans over the input. I recognize that it is 2 o'clock. I'm going to finish up the lecture. If you need to drop off, feel free to drop off. I will be around later on if you have questions. Okay, so it's just going to be another minute or 3. So we need to write everything out, read everything back in, and that is why this is called a 2-pass hash join, because we're essentially scanning all of the tuples of R twice. Once when we build the hash table, and then again when we match the corresponding buckets up. Right. So there's a third option here. If we know that the data is already organized, or for example, sorted in a particularly helpful way, we can take advantage of that as well. And this is where we get to what's called sort merge join. So sort merge join essentially assumes that the 2 input iterators are already delivering tuples in sorted order on the attribute that we are joining on. So sort merge join, like the other 2 that we've talked about, only works on equijoins, and we're assuming that the inputs are already sorted on the attribute that we are joining on. So we get the first element from each iterator, and in this particular case, it turns out that 1 and 1 join with each other. Fantastic. So we're going to produce 1 output tuple. Great. Now we're going to peek at the next element in the iterator. In the blue iterator, the next element is a 1. In the red iterator, the next element is a 2. Now this peek gave us another tuple in our result. 1 joins with 1. Fantastic. But it's also given us an extra piece of information. So now we know that, so we've seen a 2 from the red iterator, which in turn means that we're never ever going to see another 1 come from that iterator. We know it's in sorted order. 1 is less than 2. Everything else in the iterator has to be at least 2 or greater. So we're going to pause reading from the red iterator, and we're going to peek at the next value in the blue iterator. Looks like a 2. So once again, now we know that from the blue iterator, we're never, ever, ever going to see another 1. And once that happens, now we can get rid of the all of the 1 tuples out of memory, because we know we are never, ever, ever going to need them again. Now the 2's obviously join up, and we're going to peek at the next tuple behind each of them in their respective iterators. It's a 3 and a 3, so we know we're never ever going to see a 2 again, because 2 is less than 3 and the iterators are in sorted order. The 3's pair up. We're going to peek at the next element from each of the iterators. we're done with the blue iterator. The red iterator has another 3. That's going to produce another tuple. We're going to peek again, and it turns out that the red iterator is done. We've reached the end, and there are no more tuples that can be produced out of this join. So, as before, this is really nice in that it means we don't need to worry about. This is really nice in terms of I/O. Assuming our iterators are already sorted, then the merge part of the sort merge join is not going to add any extra I/O. The sort step itself might, and we'll get to that in a couple of lectures. The sort step, on the other hand, the merge step also is generally not going to need to keep all that many records in memory at a time. And again, if we ignore the sort part, the merge step is going to be really, really efficient. And of course, this has the shortcoming of the previous algorithms that we can only support equality tests. So to recap, we talked about a couple of different join algorithms. We talked about block-nested loop join. We talked about the in-memory index join, specifically the one-pass hash join. We talked about partition-based join algorithms, the two-pass hash join. And we talked about the sort merge join. Block-nested loop joins support any predicate we care about, but they do require a fair amount of memory, and they do require a fair amount of I/O, and they will have a high CPU cost. In-memory index join has a high memory cost, but a low I/O cost. Partition join has a high I/O cost, but a low memory cost. And then sort merge join has a low I/O cost and a low memory cost, but you need the data to already be sorted. So with that, we'll talk about extended relational algebra next time, and hopefully I think I have a functional way of streaming. We'll get that set up next time. Questions? Ben asks, for the two-pass hash, why did the hash function return 0 for values 1 and 2 when we're assuming pseudo-randomness for the hashing function? That is a great question. So first off, if there are two values, if there are two buckets and 3 distinct values, then at least 2 of those are going to hash to the same thing. So the value of the hash function is less that it hashes to a unique point, and more that it evenly distributes all of the values. So we're going to get hash collisions. 2 values are going to hash to the same thing. But the point is less to make sure that they always hash to the same specific value, and more to make sure that if we have 50 records, we're essentially, or 50 distinct values and 2 buckets, what we're looking for is essentially that each bucket gets roughly 25 of the 50 records. So less about uniqueness and more about uniformity. Hopefully that has answered the question. All right, apologies for going over, apologies for the technical difficulties. I think I have a way to resolve this moving forward. We'll take, another question. Is it ever acceptable to sort the rows upon insertion before running the algorithms that need sorted data? Fantastic, yes, that is a fantastic observation. So in general, when you store data on disk, you want to store it in one of several different ways. And we'll get to this a little bit more when we talk about physical layout and indexing. But yes, exactly. If you know something about your workload, then you can definitely come up with a storage layout that will optimize for that particular workload much more efficiently. And I strongly encourage you to ask Darshana about this because that is a question she will have a ton of answers for. To answer your specific question, sorting the data and storing it on disk in sorted order. The short answer to your question is that this creates a trade-off because when we insert, if we ever need to insert something into a sorted list, then that's going to cost us a linear amount of work in the size of the list. Because we're going to, unless we're adding it to the very end of that list, in which case we're really lucky, on average we're going to have to move half of the records up one slot. So if the data is changing, then storing everything in sorted order could pose a problem because we're essentially adding an overhead for update costs. But yes, it will drastically reduce the cost for reads. However, Ben, ask me the same question when we get to, I want to say, modern indexes, which is in about, I'm going to say, 2 weeks without looking at it. Because there is a data structure called a log-structured merge tree, which plays with this trade-off really, really nicely. This trade-off between the amount of work that you need to do the amount of writing work that you need to do when you insert something versus the amount of work that you need to do when reading the value back out. Deepak asks, this approach works well if the system is read-heavy on light on writing? Exactly. Yeah. If you need to do tons and tons of reads and you're barely doing any writes, then store everything in sorted order. Like I said, when we get, we'll talk about log-structured merge trees, which play with this trade-off, which are a really fun way of playing with this trade-off that is used in. I will rattle off the specific systems when we get to it, but it's Cassandra. Pretty much every column store out there uses some flavor of this. Redis, yeah, we're going to talk about it. Maybe not Redis. Oh, RocksDB is pretty much the most common example of a log-structured merge tree. Something similar happens where database reindexes in a way that is helpful in case of searches. Yeah, so one other thing that we'll talk about a little when we talk about column stores is, so column stores are a way of, a database system, an approach to designing database systems that is optimized for heavy read use, and that Solar, Vertica is another example of columnar database. Cassandra, HBase, I want to say. No, not HBase. There's like 5 different Apache projects that are all different flavors of column stores. But yeah, essentially in all of those, the data is optimized for read-only use. And in that case, in column stores, there's actually another fun trick you can play, which is breaking down the table into individual columns, in which case you sort every column on, you can sort each column independently, which, I mean, you get a lot of benefit for reads in those cases. Yeah, Elasticsearch. This is really useful for string data, just because you have to, like, string data is big, but at the same time usually ordered. So there you do get a couple of weird issues with respect to sorting strings when you want to do substring search. So looking for substrings is tricky because the sort order doesn't really help you there. And there's a bunch of different ways of getting around that. We're not really going to talk about any of those here. I'll rattle off at least two: locality sensitive hashing, and you can play around with inverted indexes. If you're interested in that, I believe I would be willing to bet that it is covered in information retrieval. All right. Again, apologies for the technical difficulties. I think I now have a way to resolve them, at least temporarily. Again, thank you, and see everyone on Tuesday.